Today we're going to learn how to graph sine and cosine. Use the unit circle to fill out the table of sine values. Press pause to do this on your own, then press play to check. Graph as many points as you can. I noticed that it starts to repeat a pattern, so I continued that to the left side. Now connect the points with a smooth curve. What do you notice after 2 pi? The curve repeats. This is called its period. The natural period of sine appears to be 2 pi, the distance between 0 and 2 pi. The function's period is the horizontal length of one cycle of the curve. If we graphed points between 2 pi and 4 pi, we'd draw another complete cycle. Between 4 pi and 6 pi, we'd have another cycle. Between 0 and negative 2 pi, you'd have another cycle. You can use negative angles to extend the curve to the left. Because there are infinitely many coterminal angles to each of these on the graph, the curve will continue forever and ever in both directions, making its domain negative infinity to infinity. Sine is a sinusoidal function, a function with smooth, repetitive oscillation. Oscillating means the function moves between two values while approaching another value. The parent graph for sine moves between 1 and negative 1 as x approaches infinity or negative infinity. So the range for sine of theta is negative 1 to 1 inclusive, because negative 1 and 1 are literally in the table of unit circle sine values. Now when we graph transformations of sine, filling out a table of values can get very complicated. Instead, I will teach you how to find and graph what I call the 5 most valuable points, the 5 MVPs. After graphing these 5 MVPs, you'll have one cycle completed. The 5 MVPs are the 5 purple points shown. Graph these below. And take note of the shape of this curve. Now fill out the table to graph cosine. Wow, cosine looks pretty similar to sine. It also finishes one complete cycle between 0 and 2 pi and then repeats, so its period is also 2 pi. Cosine is also a sinusoidal function continuing from negative infinity to infinity and oscillating again between negative 1 and 1. Graph the 5 blue points, your 5 MVPs for cosine, and take note of the shape of one cycle. Sinusoidal functions can be used to represent any of the following: sound waves, biorhythm waves, electromagnetic waves, gravity waves, tides, tsunamis and earthquakes, temperature changes over time, seasons, wheels in motion, or any type of rotation. Remember, all the values of sine and cosine come from the unit circle. Trampolines, springs, swings, Ferris wheels and roller coasters, population growth or decay over time, and many other things. So you can see why it's super important to understand the characteristics of sine and cosine graphs. Obviously, sine and cosine go on forever and ever, but it's helpful to calculate the phase shift or the horizontal shift of the function to get a, quote, starting point for graphing one cycle. To calculate the phase shift, make the argument of sine cosine equal to 0 and solve for theta. This makes your phase shift as well as the theta value of your first point equal to c divided by b. P1, P2, P3, etc. is a Rayleigh notation. I made this up to represent the theta value of each of the 5 MVPs. After finding the phase shift, which is P1, find the period of the function. Because the coefficient of the input represents horizontal stretch or shrink, it will directly affect the length of each cycle, or the period. Since the natural period of sine is 2 pi and horizontal stretch or shrink, we use the reciprocal, we're going to take 2 pi and divide by b. to get any transformed period. Now that we know the starting point and the length of one cycle, we can find the quote ending point of one cycle by adding the period to P1. Take your starting point, add your duration, and you get your ending point. Now the 5 MVPs are equally spaced, so to find the middle point, P3, we will just find the average of P1 and P5. To find the point directly between the first and third points, find the average of P1 and P3. And to find the point directly between the third and fifth points, find the average of P3 and P5. The vertical shift represents what I like to call the midline, the y value directly between the function's max and minimum oscillations. The amplitude, which is absolute value of the vertical stretch or shrink, tells you how far above the midline and how far below the midline to graph the rest of the y values. Now let's graph f of theta equals 3 sine of 2 theta. B is the coefficient of theta, which is 2, and because you're not subtracting or adding anything inside of the argument of sine, C is 0. First find the phase shift and then the period. Now add the period to the phase shift to get P5. Now use the averages to find P3, P2, and P4. Identify the vertical shift and the amplitude. Now clearly label your axes and sketch one cycle of the graph. For the y values, you can follow the formula I gave, or you can remember the general shape of the 5 MVPs for sine. For example, sine always starts at the midline. For P2, we go up the amplitude's distance, which is 3, above the midline. For P3, come back to the midline. P4 is the negative amplitude's distance from the midline, or your minimum, and P5 takes us back to the midline. Some describe the period of sine as a perfect wave or a backwards S that fell on its side. Even though you are only required to graph one period, be sure your arrows on either side truly represent the motion of the function. I decided to draw beyond one period because once you see the pattern, it's pretty easy to keep it going. Your curve should not go above the midline plus amplitude and should not go below the midline minus the amplitude. So be sure your graphs are neat. Now let's graph cosine of theta plus 5 pi thirds. B, the coefficient of theta, is 1, and C is negative 5 pi thirds, because our original formula has a subtraction symbol. First find the phase shift and then the period. Now find P5. Then use averages for P3, P2, and P4. Identify the vertical shift and amplitude. Now clearly label your axes and sketch one cycle of the graph. I don't have to label all the pi sixth angles in between my pi thirds angles, but I like to just to make sure I don't make a mistake. For the y values, you can follow the formula I gave, or you can remember the general shape of the 5 MVPs for cosine. For example, cosine always starts up at its maximum. For P2, go down to the midline. For P3, continue to go down to the minimum. For P4, go back to the midline, and for P5, return to the max. I describe this shape as a valley, but some see it as a C that fell backwards. Again, make sure your arrows represent the accurate motion of the curve around one period. We cannot draw these arrows straight upward because we know that's not where the curve goes. Try finding all the necessary information for graphing number 3, and then press play when you're done graphing or ready to graph to check. Once we've drawn and labeled our axes, remember the overall shape of a period of cosine. Cosine starts at its max, goes down to the midline, down to the min, back to the midline, and returns to the max for P5. Try finding all the necessary information for graphing number 4, and then press play when you're done graphing or ready to graph to check. You may be able to start finding the values of P2, 3, and 4 in your head. If you can do that, then you don't need to show work. Like, what's directly between negative pi halves and pi halves? 0. I don't need to show work to know it's 0. And this one actually has a vertical shift other than 0. My midline is y equals 1. I like to draw a faint dotted line to show where the midline is, just so I don't forget that it's not the x-axis this time. Once we've drawn and labeled our axes, remember the overall shape of a period of sine. Sine starts at the midline, goes up to the max, back to the midline, down to the min, and back to the midline. Oops, I almost forgot my midline is at 1 there at the end. And that is graphing sine and cosine sinusoidal functions.